Good day, everyone. My name is Chantal Janse van Vuren, and I am currently a PhD student at Stellenbosch University in South Africa. I will be presenting the paper titled Optimal Geospatial Allocation of Wind Generation Capacity for Grid Support Objectives. This paper is being presented at the International Renewable Energy Congress 2020. Introducing the paper authors, we have Professor Hendrik Johan Vermeulen, Dr. Matthew Kroch, and myself, Chantal Yvonne Janse van Vuren. Looking at a quick overview, there will be an introduction of the research proposed. We'll look at the resource dataset and focus areas. We'll also look at the South African load profiles, as well as the optimization clustered input profiles. We'll then look at the wind farm capacity allocation, as well as the impact of the allocations on the residual load profile. And finally, we'll have a look at the discussion and conclusions. This research targets emerging energy markets where optimized grid planning is essential when increasing the grid penetration levels of stochastic renewable energy resources. For this research, we specifically look at the South African region, where an integrated resource plan was established in 2010 as an adaptive strategy for energy supply up until 2030. In this resource plan, they state that wind energy must account for around 11 gigawatts of energy penetration, and solar energy must account for around 7.9 gigawatts. Now the aim is a combined 25.6% renewable energy penetration, with the current penetration levels around 7%. Currently in South Africa, wind farms are cited for maximum cumulative yield. This is, however, a problem when it comes to the minimization of residual load variance. This research therefore investigates siting to minimize the residual load variance in order to support the electrical grid. Now, when looking at the flow diagram, we see the methodology described for the proposed investigation. Here we see that the tempospatial wind speed data is converted to per unit power using the multi-turbine power curve approach. This approach was proposed by Norgard and Haltom. Now, the temporal clustering is subsequently applied to the time series power profiles for the targeted locations. The average temporal power profile of each cluster, along with the national temporal load profile data, are presented as the input data for the genetic algorithm optimization model. Now, the genetic algorithm minimizes the objective function for three defined cases to derive optimal allocations of the wind generation capacity to the geospatial clusters. Clustering is used as an initial data reduction step. This case study is performed for areas associated with the 8 renewable energy development zones. Now, these 8 renewable energy development zones are demarcated geographical regions within South Africa, which can be seen in the figure. Now, these regions are promoted by national government policy for the fast-track development of future wind and solar energy. These regions have been defined based on economic, socioeconomic, and environmental considerations. This study is implemented using the tempospatial renewable energy dataset, which was developed using a weather research and forecasting model. This numeric wind atlas has a spatial resolution of 5 by 5 kilometers, a temporal resolution of 15 minutes, and it covers a calendar year from 2009 until 2013. These renewable energy development zones incorporate a total of 3,173 geospatial coordinates. Now we look at the South African load profile. The case study is performed using the hourly South African national load dataset for the 2012 calendar year, seen in the first figure. Now the demand ranges from approximately 20 to 36 gigawatts with substantial diurnal, weekly, and seasonal variations. The second figure shows the demand profile for a week in winter. Now this profile exhibits substantial intraday variation with the worst case diurnal variation of the order of 13 gigawatts. Now these diurnal variations represent significant ramp rate requirements, and one of the objectives of the proposed optimization study is to minimize the variance of the residual load profile. Here we have a figure which depicts the clusters obtained using k-means clustering algorithm. These clusters are represented over the 8 renewable energy development zones, and the results show a large degree of diversity between the wind profiles associated with the various REDs. Now some REDs, for example Springbok and Komsberg, contain a wide range of clusters representing different temporal wind profiles. However, a RED such as Kimberley exhibits a very homogeneous wind regime. Now looking at the wind farm capacity allocation, we use the clustered map, which we saw on the previous slide, as an input for the genetic algorithm optimization allocation. Now the optimal geospatial allocation of wind capacity generation is performed by implementing the constraint optimization using the genetic algorithm. Now the genetic algorithm is a population-based algorithm inspired by the theory of natural selection. Here, a population of potential solutions or individuals evolves with each generation as new solutions are born into the population, while others die out of the population space. Now, these potential solutions improve with each generation as the general fitness or accuracy of the population improves. A selection process then identifies the best individuals for breeding with other individuals, and this is based on their fitness values to produce new candidate solutions within the population space. Random mutation is also incorporated into the algorithm to introduce variation in the parameters of the individuals. The algorithm is repeated until the desired termination criteria is achieved, and once the algorithm terminates, the candidate solution with the highest fitness value in the population is selected as the solution to the problem. So in this figure, we see, after running the optimization methodology, the wind generation capacity allocations obtained for the 3 case study objectives. Now here we see that the 3 case studies is maximum capacity factor, minimized residual load variance, and minimized peak load. Now for the case study aimed at maximizing the capacity factor, the optimization algorithm predictably allocates all capacity to a single cluster, and this is the cluster with the highest cumulative annual yield. Now for the case study aimed at minimizing the variance of the residual load, the optimization algorithm spreads the allocation to leverage the diversity between the clusters. And we also see that all clusters are allotted an allocation. Here we see that cluster 6 receives the largest portion of the allocation, and we can see that this is 2.41 gigawatts. Now the remainder of the wind generation capacity is dispersed among the remaining 29 clusters, each of which are allotted less than 1 gigawatt. Now for the case study aimed at minimizing the daily evening peak load, the capacity is distributed between 3 clusters with allocations of 1.08, 8.94 and 0.1 gigawatts assigned to clusters 18, 21 and 26 respectively. So now we look at the impact of the allocations on the residual load profile. So here we see in the figure the average daily profiles for the national demand and the residual load of the optimized case studies. Now minimizing the evening peak load results in a large average reduction in the residual load during the peak period. This yields an average daily evening peak load that is of the order of 1 gigawatt lower when compared to the case study for minimizing the variance of the residual load profile. Here we see that the morning peak period residual load is, however, considerably higher compared to the optimized evening peak, which is not ideal from a grid perspective. Now this suggests that an objective function that targets peak periods should ideally consider both peak periods. Now, of the 3 case scenarios, maximizing the capacity factor delivers the lowest morning peak but the highest evening peak. Now, this is clearly not an optimal result from the perspective of the variability of the average residual load profile. Now, overall, the results show that the residual load profile can be manipulated effectively by optimizing the geographic capacity allocations of wind generation resources amongst wind regime clusters. We see that a substantial reduction in ramping can, for instance, be achieved by siting the generating capacity such that the variance of the residual load profile is minimized. Now, for a system that is subject to generation capacity constraints in terms of the dispatchable generation fleet, as is the case for many developing economies, the required maximum generation can be reduced. To conclude, this was an exploratory study of the potential benefits of optimizing the geospatial allocations of wind generation capacity in the context of various grid support objectives. Now, the optimal geographic capacity allocations are derived using the genetic algorithms for 3 objective function case studies. These 3 case studies include the minimization of the variance of the residual load, minimization of the residual load during peak load periods, and minimizing the total residual load. The results show that the residual load profile can in fact be manipulated effectively by optimizing the geographical capacity allocations for the wind generation resources amongst wind regime clusters. Thank you.